Hey everyone, this is a video lesson that I will be using as a supplement in my AP Calculus AB class. However, I'm putting it online just in case it would be helpful to anyone. As usual, I put a link to a printable guided set of notes in the description of this video that I encourage you to use to help follow along with what I have in this lesson. Okay, so this is really exciting. We are starting chapter 3, what my textbook calls chapter 3, and that is all about derivatives of functions. In this first section, we will be discussing the definition of a derivative and taking a look at that definition in two different forms. Now, whenever I get to this chapter, I have mixed emotions. I, of course, feel so excited because we're about to embark on something that is amazingly crucial to understanding calculus. However, it's also a little bit scary because this chapter is 9 sections. Yep, you heard me. It's 9 sections. And every year I think about, okay, how can I condense or combine to try to make it into something that is not so gigantic? And I'll tell you what, the only thing I can think of is taking it into 8 sections. That's the best I can do here. Okay. So it's sort of a long journey. And in addition to being so many sections, looking at this first section, 3.1, I realized that I'm probably going to need to make at least 4 video lessons because it just makes sense with what we have to cover in this section. All right, so I apologize for that, but you know what? It's kind of like I was talking to my daughter the other day. She's about to get braces, and this is kind of like getting braces, okay? What I said to her was, it's going to be a little bit painful. It's going to be a very long process. However, what you get out of it is going to be so fantastic that it's worth it all. All right, so I don't know if that sounds like enticing at all to you, but let's try to enjoy this long road that we have ahead of us, and what you're going to learn out of what we will do here, it's all worth it, I promise. All right, so what we're going to do to start is take a look at the definition of a derivative that you have seen actually a couple of times now from some other lessons. It might look a little bit different, and we'll talk about the difference, but first let's just read it. Okay, so we have a derivative of function f with respect to the variable x is the function f prime. Notice it tells you how to read that, whose value at x is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Now, I would like to remind you that what you are looking at right here is actually coming from the slope formula between 2 points. Okay, so you can say that the formula that you're seeing, which we call the definition of a derivative, it is a limit of a slope between 2 points converging into 1 point. Okay, I will review that in a moment, but for right now, we're starting with this formula because it's extremely important to what we're going to do today. All right. Next, I just would like to share with you some notation. Okay, one of them we already discussed. Just remember that this little apostrophe, when you see that on a function, you read that as prime. So we would call this, let's see, make sure my pen's set up. We would call this f prime of x. Okay, when you see the apostrophe in calculus, you read that as a prime, and it indicates that you are showing a derivative. The next one would be y prime. The last 3, you see lowercase d's, dy over dx, df over dx, d over dx, parentheses, f of x. This one in particular, we'll talk about this notation in the third video when we discuss having a function and then deriving it, taking its derivative. So you'll see that again in the third video. But all of those are sort of just a play on the variation of, it's just like a variation, I should say, of delta y over delta x, which is one way that you can show that you are doing slope between 2 points, change in y over change in x. However, the delta was changed to a lowercase d, indicating that you are actually doing a infinitesimally small change in the function, because you're taking 2 points and putting it into change at 1 point. Okay, so let's review that right now with this little graphical component here. If you are following along with the guided notes, you might just see a set of axes, I believe. I think that's what it is on mine. It's just a set of axes. And so you might want to pause the video and take a moment to draw in. The way that I always tell my students to do this when we're in class is I say draw the blue curve first. Okay, so we're just starting with like a standard curve, some sort of curve, curved function, f of x. Okay, and then you'll want to pick 2 points. Okay, I'll highlight here. You'll want to draw 2 points, you know, approximately like right here. And if you need to take a ruler or a straight edge or something, draw a line between those 2 points. Okay, that's called the secant line. It goes through the curve in 2 places. Then you can label the coordinates of each point. So the coordinates of this point are x, comma, f of x. And the coordinates of this point are x plus h, comma, f of x plus h. And then this h is just showing you that it is the distance along the x-axis between the 2 points that you've established. And so what I'm going to do right here is I'm going to write those ordered pairs. So the first point I wrote as an ordered pair x, comma, f of x, and the second point I'm writing as an ordered pair x plus h, comma, f of x plus h. You know, this is like x1, y1, x2, y2, just 2 ordered pairs. If you're familiar with that, you might even want to just like label it here, because that might be something that you're used to seeing from, you know, way back from Algebra 1. And then we are going to set up, what I want to do next is set up the slope of the secant line, which this is all just, you know, basic algebra. You know, the notation might be a little bit strange, but we're just showing here that we're doing the slope between these 2 points. So I'm going to follow the slope formula. In the numerator, it's y2 minus y1, change in the y, right? So I'm going to write that as f of x plus h minus f of x. In the denominator, it is the change in the x, or x2 minus x1, so x plus h minus x. Okay, so we just showed that we can take 2 points on a curve, we can draw a secant line through those points, and we can find the slope of that secant line, right? Those are all things that we should be able to do fairly easily. What a derivative is it is saying, let's do that process, but with just 1 point. Let's make it into 1 point. Okay, so what I'm going to do next is I'm going to grab a different color. I'm going to go down to this initial point. I'm going to label it again, and I'm going to try really hard. If you watch my videos, you know that I struggle with this. Let's make it a red line. All right, let's see if I can do this. So I'm going to draw a line that hits the curve just at that 1 point. I'm going to try to make it a long line this time, because my secant line's kind of long. Yay, I did it! That's not bad. I'm proud of myself right now. All right, back to my pen. So now, what we're going to do, actually we can leave it at that, okay, there we go. We are going to write a slope formula for this line, which is called a tangent line. I should put that right here. The red line is a tangent line. Okay, and this is where we're going to get the definition of derivative that you wrote on, you know, from the initial slide. How do we take this secant line formula and turn it into the definition of a derivative? Well, there's one thing that's definitely going to happen here. the x and the minus x add to 0, right? So we can cancel them. So we have, by the way, you can't do that here. Okay, f of x plus h minus f of x. No, don't cancel anything there, please. It's a very different thing than x plus h minus x. So we have f of x plus h minus f of x all over h. The last part, okay, maybe you know what it's going to be because you already wrote it, but let's talk about it. The last part, I'm going to move this over a little bit, is turning the 2-point formula that we have up here into a formula that will work at just 1 point. And the way we do that is we put in this really crazy thing called a limit. It says, all right, you can't really use the slope formula for just 1 point, but we could, get as close to doing that as possible by making this distance between the 2 points, which we call h, go to 0. If you make h go to 0, and, you can't really do that. Ugh. Sorry, I clicked a button. But that's what a limit's for. A limit's like, yeah, I know you can't really do that, but let's just do it anyway. Let's just see what happens here. All right. And there's your formula that is the definition of a derivative. So it is the formula that you are going to use whenever you're asked to find a derivative. It's the formula that you're going to use whenever you're asked to find a slope of a tangent line. It is the formula that you're going to use if you are asked to find something like an instantaneous rate, because an instantaneous rate is 1 point rate of change, right? Which would be slope. So there we go. We kind of developed it so that you can see, hopefully you can understand where this formula is coming from. Okay. Now for the rest of this video, I just want to take some time to use it over and over again. Let's practice setting up our points and the formula and doing the limit as h goes to 0, so you can see what that looks like for different types of functions. So this is sort of just an extension of what we did in section 2.4 when we talked about instantaneous rates. We're just doing the same here to get used to it. Okay, so let's take a look at example 1. Find the derivative of the following functions at the given points, and you're going to see like a part A, a part B, a part C, a part D, and I believe a part E. Yes. Okay, that's what we're going to do today for the rest of this video. Example 1, A through E. For example 1a, we have y equals x squared at a equals 7. Now, when we saw, I'm going to back up for a minute. When we saw this formula in section 2.4, I don't know if you notice a difference here. When we saw it in 2.4, these were a's right here, the letter A instead of x. A is an x coordinate. It's just a specific x coordinate. So don't let the letter system like throw you off too much. When you're given a function and a value like this and you're asked to find a derivative, that value is going to be your x coordinate. We could change that to an x if you'd rather not have the A there. You could call it x. Sometimes I have students even call it x1 because they like setting their points up as x1, y1, x2, y2. So it's up to you, the notation you use whatever makes most sense to you. But, here's what I suggest you do with this type of problem. You set up, first of all, you draw an actual parenthesis, not whatever that was. You set up an ordered pair with your given x coordinate, and let's fill that in here. When x is 7, y is 7 squared, which is 49. You can even label that x1, y1 if you would like. And then the second ordered pair, okay, this is like key. How do I get another ordered pair? I only have one x coordinate. The second ordered pair will always be that x coordinate plus h. Just add an h to your x coordinate. Now, do not just put plus h on the 49. Okay, think about how you get a y coordinate after you have an x coordinate established. You take that x coordinate and you sub it into the function, right? So what we have here is 7 plus h quantity squared. Okay, I don't see that a lot, that students just take the 49 and add an h, but like sometimes my mind goes, oh my gosh, a student might do that. So I have to say it. I'm sorry, I have to say don't do that. There's your x2, y2. And now at this point, it is up to you how you show your work, where you do your, I call it like, side calculations or whatever you need to do. Like a lot of students from this point might just jump into the slope, which you can call, you have all sorts of options here for what you want to call it. I'm going to call it y prime. You call it m, you could call it f prime parentheses 7 dy over dx. Lots of options here. I'm just going to stick with good old y prime. It's nice and easy. And then the very first thing is always, let's write the limit as h approaches 0 of the slope between these 2 points. y2 minus y1 over x2 minus x1. Some students say, come on, we've seen so many of these. We know that this 7, this minus 7 are going to cancel. Can we just put an h there? Sure. Yeah, right? Like that's right there. So go for it. I just like to show when I set these up that I'm just doing slope between the points that we established. All right, now what I mean by side calculations is like right here. This is what you're going to need to work on because, yeah, that's going to happen, right? H in the denominator. But this is what we need to work on now. 7 plus h quantity squared. You need to distribute 7 plus h times itself, FOIL, whatever you want to call it. And you would get 49 plus 7h plus 7h. Let's combine that to plus 14h plus h squared minus 49. So just so that we're clear, this is not 7 squared plus h squared. It's not 49 plus h squared. It becomes that because you have to take the binomial times itself. Oops. All right, now let's work on seeing the good stuff. And that is the fact that 49 and minus 49 cancel, right? Also, there is an h in the 2 factors that remain in the numerator, so you can factor that out, because then this happens, right? Okay, this is all stuff that if you've watched my other video lessons, you've seen this before. If you're in my class, we practiced it a whole bunch before even doing it here. And so now we have the limit as h approaches 0 of 14 plus h. And we can use substitution to sub 0 in for the h that remains and get a derivative value of 14. Okay, so I'm going to write this as 4y equals x squared at x equals 7, y prime equals 14. You don't have to always write an answer like that, but I kind of like to show it just to see what did we do. We took the function x squared, we looked specifically at the point x equals 7, and we said the slope of the tangent line at that point, the derivative value is 14. Yay! All right. If you watched my intro to derivatives, my Calculus Just Explains It All derivatives video, you'll know that I already let the cat out of the bag about y equals x squared. It is a little shortcut that you can always take the x coordinate, the given x coordinate, and double it, 7 times 2, and that will give you the derivative value. Okay, so we're going to prove that in the 3rd video of this section. And after we prove it, we're just going to use that instead of this formula to get any derivative value of y equals x squared. Okay. However, okay, even though I let the cat out of the bag with y equals x squared, the good news is that there is still so much fun to be had because the derivative value being times 2, like the x coordinate times 2, that's just for y equals x squared, people. There's all sorts of other functions out there. And so there's all sorts of mathematical secrets that you're going to still need to find and figure out by putting a function into the definition of a derivative and seeing what you get out of it. Okay, there are all sorts of shortcuts out there. Okay, it's just we need to find them. And the way we find them is we put them through the derivative definition and see what we get out. So like what I'm telling you is as we move on to part B, again, I'm going to change this to x. You can say that's just an x. The shortcut is not multiply by 2 for this one. Okay, it's a much different set of operations. And so let's not just say, well, it's probably going to be 2. 1 times 2. No, let's do the work of getting our ordered pairs set up. Let's see, 1 squared times 2 plus 3 times 1. 5 is the y coordinate, right? Filling 1 in here. And then remember, right here, it's just 1 plus h, comma, okay. Take that 1 plus h, and you're going to replace the x's with 1 plus h to get your y coordinate. So it is 2 quantity 1 plus h squared plus 3 quantity 1 plus h. It looks a little weird. I'm sorry. Let's try to fix that. This is why, like, every single one of these videos will be an hour long. I'm sorry. If you're rolling your eyes at me, I'm rolling my eyes at me too. All right, and again, this is just x1, y1, x2, y2. All of that, that is all y2. So we will get y prime from the limit as h goes to 0 of y2. Oh. Let's try that again. Y2 minus y1 over x2 minus x1, which is 1 plus h minus 1, which will just be h. We will just simplify that step right there. All right. So the main thing we need to work on here is, keep in mind, your goal is to get the answer to this limit, evaluate the limit at this point. 0 needs to go in for h. That can't happen clearly right here. You're going to get 0 over 0, which is important to note, I guess. Yeah, it is. But I'm not going to show that work right now because I'm trying to cut down on time a little bit. So what you need to do from this point, let's write that limit, is get this 5 to cancel. That's kind of important because then that'll lead to getting this h to cancel. That h needs to get out of there. So what we're going to do here, and this is, when I was talking about like side calculations, I don't know how much of this you want to write in your work here, or if you just want to do something like this. We have 2 times the quantity 1 plus h squared plus 3 times 1 plus h. I keep forgetting that 1 there. All right, so let's FOIL this, and we have 2 times 1 plus 2h plus h squared plus 3 times 1 plus h. See, I did it again. There's a 1 right there, okay? Let's distribute, and we have 2 plus 4h plus 2h squared plus, let's distribute the 3, and we have 3 plus 3h. Finally, I'm going to combine like terms, and I'm going to put that stuff down here. 2 plus 3 is 5. 4h plus 3h is 7h. I did those together. I did these together. Now I have just a plus 2h squared. Bring along the minus 5, and then all divided by h. Can you see what's going to happen? The good stuff, right? 5 minus 5 adds to 0. Let's bring down that limit of, oh, let's do this as well. There's an h, there's a common factor of h in what is remaining in the numerator. So you can divide that out. Divide those h's to 1, and we have 7 plus 2h left, where we can sub in 0 for h. So we get y prime equals 7. All right, so this is where I love to be in person with my students who are just learning this for the first time, because we say for y equals 2x squared plus 3x at x equals 1, y prime is equal to 7. And I say, okay, I'll tell you what, there is a shortcut. Ooh. There's a shortcut to finding that answer. Can you figure it out? And I see some really thinking about it, and that's what I love to see. They're like, ooh, maybe I could figure out the shortcut. And what I mean by a shortcut is there's something you can do to this function and then just plug 1 in, because that's our given x coordinate, and get out an answer of 7. I love to see my students like think about it and try to figure it out. I'm not going to tell you what the shortcut is right now. I'm going to leave you on that. And, you know, at some point you will know them all, I promise. And you won't have to use this formula anymore. It's just right now, because we're in the infancy of learning derivatives, this is what you use to get your values until you know all of those quick and easy little shortcuts. All right, maybe I should like look up my stuff to make sure I'm doing what I need to be doing here. All right, so we're going to move on from quadratic examples and take a look at a couple of other different types of functions now. Take a look at this next one, part C. Y equals 1 over x at x equals 3. Call that whatever you want. It's just an x coordinate. Okay, so let's set up our ordered pairs. 3 comma, sub 3 in, and you get a third for the y coordinate. Here's your x1, y1. If you remember that that's what you need to do to start, and I'll tell you what, not all teachers teach it like this, where we set up the ordered pairs and then move into the formula, or the definition of derivative. Some teachers just say, let's just jump straight into that definition. I just feel like this is a good starting point, because it just is not so scary. It's like, oh, I just need to set up my ordered pairs and then show the slope between those 2 points and do the limit as h goes to 0. And okay, I can do that, right? Like, this is just a process. 3 plus h and 1 over 3 plus h are the coordinates of the second order pair. So y prime will come from the limit as h approaches 0 of 1 over 3 plus h minus 1/3, all divided by, 3 plus h minus 3, but that will simplify to just h. All right, now I do concede that even, you know, even if you're able to set this part up, this one does look very different. It might look a little bit scary because we have this complex fraction thing going on. And there's all sorts of ways that you can work with this to get the limit evaluated. You definitely can't sub-zero in right away. You will get 0 over 0. But I'm going to actually show something different that I actually saw on a, I forget where I saw it. I saw it on an Instagram page not too long ago. I want to give you credit, but I can't remember where. I'll give you credit in my Instagram story if I remember who it is. But here's the little shortcut. You're taking this difference divided by h, and so really that means you need to have this divided by h minus this divided by h, right? So that's not usually something I do. I usually leave it in this complex fraction form for a while, for a couple of steps, but I'm going to suggest you do this. Okay, it's just sort of a thing that I saw, and I was like, oh, Yeah, we could do that. That kind of makes it not so scary right away, right? So I just took this h and I put it here and here, right? There's that h, there's that h. You can do that. And so now what we need to work on is getting a common denominator between these. They both have a common factor of h, but what we need is a factor of 3 plus h over here. We need a factor of 3 over here. So what I'm going to do, oh, I forgot to write my limit. I'm going to just write it in the next step. Don't forget that limit, please. What I'm going to do here is I'm going to multiply this fraction by 3 over 3. 1 times 3 is 3. And that puts a factor of 3, which we need because we see this factor of 3 here in this fraction, minus. Now I'm going to multiply this fraction by parentheses 3 plus h over 3 plus h. Make sure you keep the parentheses around the 3 plus h in both parts. And it looks like that. Now we have a common denominator between our two fractions, and so we can, let's move down here, write the limit. We can combine these fractions into one difference over that common denominator. So now the common denominator is this, and we're going to take 3 minus parentheses 3 plus h, or you can distribute this minus, excuse me, what just happened to my voice? Okay, you can distribute this minus here and here. So I'm going to write 3 minus 3 minus h. This is a huge mistake that I see with beginning calculus students, is that they forget to distribute the negative to this positive h over here, which you need to do. And so now we can do this. 3 minus 3 goes to 0. We have negative h in the numerator over 3h times quantity 3 plus h in the denominator. And now we can do like a little clutch move like that, which will allow us to sub-zero in the next step. Take a look at what we now have from canceling the 3 minus 3. That then allowed us to cancel the h in the numerator with that one factor of h in the denominator. And now there's nothing holding you back from subbing 0 in to the h that remains, because you will not get a 0 over 0 answer. You will get what? Negative 1 over 9. There it is. Ooh. Instead of boxing that in, sorry, let's write it out. For y equals 1 over x at x equals 3, y prime equals negative 1 over 9. Now, just as I told you with the last example, there is a shortcut to getting this answer. If you take this function, do something to it, plug in x equals 3, you will get that out very quickly and easily. The question that we're going to be dealing with eventually, or you can start to deal with on your own, is how do you do that shortcut? If you don't know the shortcut, you're just going to do this forever. No, we'll figure out the shortcuts eventually. All right, I may skip a little step in this one just to make it go a little bit more quickly, and if you need additional help with the step that I skip, you can ask me about it on your own. It's going to be the cubing part. All right, but let's just start this one like we start every other one. Let's set up our ordered pairs. X is 2, comma 2 cubed is 8. Add an h to your x coordinate and sub that x coordinate into the function to get the y coordinate. Start your formula. y2 minus y1 over x2 minus x1 will always simplify to h. All right. Now, here's the part that I'm going to sort of gloss over a little bit just because I don't want to waste too much time discussing an algebraic technique that you could probably figure out if you work out a little bit on your own here. You need to expand 2 plus h cubed. That means taking 2 plus h times 2 plus h times 2 plus h. Now, I'll tell you, that process is take the 2 plus h times the 2 plus h, okay, FOIL, and then distribute the third 2 plus h through your trinomial. All right, so I'm going to set it up here, but I'm not going to actually do the work. I'm just going to, show you what I'm saying, I guess, and then take you to the end result. So 2 plus h cubed looks like this, expanded, and then you would be foiling here, and then distributing this 2 plus h through. Okay, that's something that I usually just tell my students, work on this, and then let's come back together in a moment. I'm just going to go straight to, what do you get out of that? You get 8 plus 12h plus 6h squared plus h cubed. There's a minus 8 from over here, and there's an all divided by h. Ooh, look at that cute fraction bar. Called an integral fraction. No, it's not. All right. And now, now that that was probably the trickiest or most tedious part of this, we're ready to just do this kind of stuff. Another reason I love being in the presence of my students when I do this is because at this point, I'm doing it on the board and I turn and I look, and my students are just all doing it on their own, or they're done. And they're just watching me like, you clown, how are you not done yet? And it just makes me feel good. It's like, okay, you guys are getting the hang of this. All right, so we did canceling. We did more canceling because we had a common factor of h up here that we could do that stuff that we usually do. This is really good teaching right now. Do stuff, right? That's a 0 right there. And we get a y prime. This is all y prime of 12. I'm just going to write that up here. So 4. This is kind of an important one if you're really serious about figuring out the little shortcut that could be used for all of these that we've been doing. This is an important one to ponder. For y equals x cubed to x equals 2, we get a y prime value of 12. Like, where's the shortcut? What do you do to this, then plug in this to get that? What's wrong with me? I'm trying to draw a box. Never mind. It's just not happening today. My spatial brain, my brain's not spatial. All right. Oh gosh, we made it. We made it to part E. Thank goodness. Just in time. Okay. For this last one, y equals 2x plus 5. I really hope you can just tell me the answer. I'm not going to set up an ordered pair. Well, there's not even an ordered pair given, or an x coordinate. Do you notice that? There's no x coordinate given. Do you know why? Let's think about this. This is like testing. Do you remember what we're doing here? Where does all this come from? Instead of just being a mathematical process that you just remotely or routinely go through. What's going on here? Y prime is equal to what for any x coordinate? This is a line. We're doing slope, right? Every single point along this function has the same slope, has the same rate of change, and it is 2. Oh, yay, that one's done. It's the slope, right? This is y equals mx plus b. There's your slope. So that's your derivative. Yay. Okay. So just so you know where we're going for the rest of this section, in the next video, we will be discussing an alternate definition. It's just another option that you can use to do this process, all of this stuff that we've been doing. So we're actually going to do a couple of the same problems over again with what's called the alternate definition of a derivative. Okay. And then from there, we will, in the third video, start to discuss these shortcuts to finding derivative values so that we actually don't have to use either definition, once we establish what those shortcuts are. Now, you're not going to learn all of them. That's what, like, the 8 or 9 sections of this chapter is mostly about. It's about figuring these shortcuts out and these little rules. But we'll see a really important one here by the end of this section that you'll be able to use throughout the rest of the chapter. Okay? I hope this was helpful. Bye.